Okay, so good morning, everyone, and welcome to this NEASQC webinar dedicated to our use case on hard optimization problems for smart charging of electric vehicles. I'm Pascal Bernier-Brunel. I'm the communication manager of NEASQC, and we are going to have today as our speaker Pascal Bendotti from EDF. But before we go on into today's subject, I would like to say a word about the series of webinar. This webinar is one of a series, and we started about a year ago. And all of our webinars have been recorded. So really, if you want to listen to what we've done in this past year, you just go to our YouTube channel, and you will be able to listen to our webinars. So we've organized those webinars to share the findings of the project, the findings of the different use cases with you all, with the quantum computing community, and also to share our libraries and tools that we make available. We are getting to the end of the project, so we'll have 2 more webinars. I don't have the dates yet, but you will receive an email to announce the exact date. So in October, we'll have a webinar about quantum rule-based systems for breast cancer detection, and then later on we'll have one about quantum natural language processing. Sorry, I'm trying to admit everyone as I talk, and it's a little bit complicated. So let's get to today's subject. So first of all, I would like to welcome Pascal Bendotti. She's expert research engineer at EDF R&D. So hello, Pascal. Thank you for being with us today. And before I hand over to Pascal, one last word concerning the related publications. There is an upcoming deliverable from our project that will be available in October, and it will be available in our use case page. So if you're interested, stay tuned, and you will have the opportunity to download this. So now I will hand over to Pascal. I will stop sharing so she can share. So now you can share, Pascal.
Okay.
So while Pascal is sharing her slides, I wanted to tell you we will take your questions, but after the presentation. So you'll be able to ask your questions either in the chat, or you'll be able to raise your hand, of course. So Pascal, are you ready?
Yes. Do you see the first slide?
Yes.
Okay. So I guess we are ready.
Yeah, off we go.
Ready to start. Okay. So today I will be presenting some results relative to the solving of a smart charging special case with a hybrid quantum classical decomposition scheme. This work was completed by Margarita Veshchezerova during her PhD with Marc Veshchezerova at EDF. Oh, okay. Now I cannot move. No, so I guess I have it. I don't know how I did the first time because I cannot. I'm stuck with the first slide, so maybe next slide. Let's see. Okay, do you see the next slide or not? Could you tell me if you see the second slide? Because
we see aim of the. Yep.
Okay, so it will be not the best way to do it, but it will work. Okay, so the aim of the project was to focus on hard combinatorial optimization problem coming from energy management due to EDF, of course. So here we concentrate on the smart charging of electric vehicle as a use case, especially because of the increase of electric vehicle, which makes a great application for large-scale combinatorial optimization problem we need to solve at large scale. And also we did some previous experiment on the quantum approximation algorithm, which show good results. So we wanted to keep going and use it to expand the span of application on which we could use it. And we developed a generic open source library, as it was mentioned earlier. So as you all know, one major limitation in the NEASQC era is the required number of qubits that scales linearly with the number of binary variables involved in the classical formulation of the problem. And the thing is that such formulation, even when they are compact, meaning polynomial in terms of number of variables with respect to the size of the original instance, they are not only linear, but they could go polynomial. So it could mean quadratic in terms of number of variables. So because also of the scale of the instances in the industrial context, this could rise up to several millions in the large scale applications. So for this reason, clearly, it's not possible to benchmark quantum algorithm against their classical counterparts. So the proposed alternative here is to rely on a quantum classical hybrid approach. It is already the case for the quantum approximate optimization algorithm, but the thing here is to go one step ahead and to integrate a quantum algorithm in a classical decomposition scheme, especially to solve the difficult subproblems specialized in the combinatorial parts. So the outline of the talk will be first to present the problem by itself, with the smart charging use case, and which reduces to a maximum independent set, as I will show. I will recall some preliminary results we obtained on quantum approximate optimization algorithm and its variant, the recursive QAOA algorithm, which was used to solve the maximum independent set. And then we will expand to include it in a hybrid quantum classical decomposition scheme, and I will go in more detail on this aspect. So first, I'll go for the smart charging presentation. So the problem is that each car needs to be charged at a given time interval defined by a user ahead of time. So it's the interval which is given. And the problem is to serve the maximum number of cars on one terminal. And there's an additional constraint which says that the cars are in groups, and we need to partition the interval set representing each car. And in this case, we could reduce the problem to an interval scheduling problem. So in this case, we have each job is defined as an interval, so corresponding to the charge interval of one vehicle. We partition the set of intervals into groups with at most k jobs per group. And a subset of interval is said to be compatible if the two constraints are accounted for. So no two intervals should overlap, and no two intervals belong to the same group. And then the group interval scheduling problem is to find the largest compatible set. So on the right, you can see like some intervals, and we could design a conflict graph. So each interval is represented by a vertex, and an edge would be drawn between two vertices if they do overlap. And in addition, we have the group constraints, which define clicks for the corresponding intervals involved in the group. So here we have like an instance with with 3 groups of 3 vehicles each. And that would be an instance of the group interval scheduling problem. And for at most k jobs per group, the group interval scheduling problem is NP-hard for k greater than 3 and is polynomial for k less than 2. And this problem is equivalent to solving a maximum independent set on a graph, a special graph, which is a group interval graph, as I explained right here. Okay. So, what did I do? Okay. So the connection, there's a connection with the graph coloring problem we will be interested in. And especially if we want to assign the electric vehicle to a minimum number of terminals. So far, we were interested in only one terminal and to assign a maximum number of vehicles to this terminal. So here, this problem reduces to the graph coloring problem. And for a number of colors greater than 2, then the problem is also an NP-hard. Obviously, there are strong relationship between the graph coloring problem and the maximum independent set, as a color is assigned to a set of independent vertices. So in Violin, we have like one maximum independent set in this graph. So basically, there would be one vertex per group, so per color here. And also the vertices in the maximum independent set could not belong to the same edge. So we have a second independent set in orange. And then we could define a third independent set, which is a smaller cardinality, it's 2. And this graph is colorable with 4 colors, especially because the black, the last vertex needs an extra color. So this will be the problem we'll be interested in to be solved in decomposition scheme. But first, I will review the preliminary result we obtained using QAOA algorithm, I mean, its variant in the recursive form for the maximum independent set. Okay, so QAOA is a variational quantum classical heuristic, and it adapts the idea of the adiabatic algorithm to the universal gate-based quantum computers. So it's designed to find an approximate of the ground state, which is actually to find the low energy state of an Ising Hamiltonian. So it can be applied to optimization problem if we can map the objective functions and the space of solutions to a Hamiltonian, and especially to a subset of basis states corresponding to an n-qubit system, for which the solutions are feasible. So the idea is for each feasible solution of the original problem, we need to match the eigenvalue of the Hamiltonian with the objective values of the original problem. So the mapping is quite straightforward in the case of the quadratic and constrained binary optimization problem, the QBO, especially because, as the name says it, there are no constraints. So usually in a combinatorial optimization problem, there are lots of constraints. So in this case, we would need to relax them in the objective function, which is the main difficulty to deal with this technique later. Okay. So unlike in the adiabatic algorithm, QAOA dynamics is ruled by a sequence of pulses that jumps from the initial Hamiltonian to the final Hamiltonian, which actually correspond to the solution we are interested in. So the number of pulses we need are called depth, and it's a predefined user parameter. So basically, the QAOA applies a series of phase separation and mixing in alternate manner. And if the depth is large enough and also the time, then we have like a guarantee that the approximation improves and tends to reach the optimum. But practically, P is really limited, as well as the time of simulation. For this reason, usually we cannot expect to reach optimality. So the classical part determines the optimal values for the parameters beta and gamma, minimizing the expectation. But there are difficulties related to the search of the beta, the angles beta and gamma. It involves nonlinear classical techniques with a local minimum and also flat area like barren plateaus. So it's quite difficult to have them, to have the optimal values and actually to find good values. And the quantum part actually prepares and measures the states. And this implementation calls for a quantum computer. As in the pictures, we see that in the green, the classical part, and in the pink, the part which requires a quantum computer. In fact, we used a recursive QAOA algorithm instead, especially because we're facing a low-depth QAOA circuit. And in this case, we deal with the locality restriction, meaning that in the circuit, we could see only the first neighbors, which restrict the potential of the algorithm to find the optimum. So using a QAOA, we could circumvent this difficulty. So we used QAOA's parameterized state and performed a recursive variable elimination. And in this case, we can fully simulate the circuit with the P equals to 1 using analytical expressions, which was not possible with a QAOA. And that's what has been used in simulation. So for the maximum independent set problem, we go from the linear program, which is in its naive form, really easy to understand, especially because we want to maximize the number of vertices in the independent set, provided not two vertices belonging to the same age would be in the independent set. So that's the first problem, really easy to understand. And also in the QUBO, which agrees with the Hamiltonian form. So we relax the constraints and put it in the quadratic form, and then it appears a penalty. This penalty should be sufficient to ensure that the non-independent set would be suboptimal, so that the optimal solution would be feasible and would be an independent set, a maximum independent set. So because quantum heuristics do not return an exact solution, but rather some low energy state, then we need to increase the value for lambda. And actually, we cannot go too far, especially because then it would flatten the energy landscape around feasible solution, and then we would reduce the performance of the algorithm. For choosing a good values, then there are different algorithms, and one is the bisexual search from the literature, which could help to fix the the values. So the result which were obtained. So first, we considered an exact algorithm based on the branch and bound approach, and we could use it up to 500 in terms of number of vertices. So on the left, we represent in the x-axis the size of the instance, the number of vertices, so up to 500. On the y-axis, it's the approximation ratio with respect to the exact algorithm. And in pink, it's the recursive QA. In green, a greedy algorithm like Desature with a local search, which is improving the basic greedy solution. So we see that up to 300, something like 300, almost 400. Basically, there's no winner. We could even say that, well, it's difficult to say that one algorithm is better than the other. On the other hand, between 400 and 500, the red solutions corresponding to the recursive QAOA seems to outperform a greedy algorithm and improves the approximation ratio. On the right, it's another representation, but it goes beyond 500. We try to solve up to 900 vertices, but beyond 500, we do not have the reference of the exact algorithm. So our QA is exact up to the yellow vertical line with the depth p equals 1, and beyond there is no guarantee. So in blue, the greedy algorithm dominates, while in green, the QA dominates. So it's a better option. So here we can see again that between 400 and 500, the green beats the green, but beside this area, it depends on the instance basically. So it's not a perfect results, but availability of quantum computers to implement their QA with a depth greater than p equals 1 should improve these results. And also, what we could do right now with this algorithm, limited to a depth of p equals 1, is to improve the initialization of an exact algorithm. Because usually, Desature, for instance, the greedy approach is used to initialize an exact algorithm. And the idea is to add the contribution of the quantum algorithm when it helps. For instance, when the greedy algorithm find a solution, and then we can try to improve it using a quantum algorithm. And that's exactly the idea we'll be using in a decomposition scheme. So I'll go for the hybrid quantum classical decomposition scheme. So basically, we'll be using this approach, especially to solve the graph coloring problem, because it's not only the problem is not only to find a maximum independent set, but obviously to combine different independent set to cover all vertices with a combination, basically. So it will involve even more binary variables, and this cannot be taken into account with the quantum algorithm. So one approach in the literature is to use a decomposition scheme, especially the first part of the decomposition scheme, as a heuristic for the combinatorial problem. Well, well, sorry, I didn't. That's the next slide. Sorry. So what I said first was the first aspect, and that's what we'll be addressing. Okay, so sorry, I did not remember my slide. So the first shortcoming comes from the number of qubits. So I said that already. That's why we will be using a decomposition technique. And also the other aspect is the relaxation of constraints. And we will be using decomposition techniques to solve the large-scale instances that cannot be solved otherwise. And recall that such techniques are also used in the classical context, especially to deal with too large instances. Okay, now I'll go for the principle, a description of the principle of the classical branch and price scheme. So the branch and price scheme is a branch and bound method, and at each node, column may be added to the LP relaxation. So usually, in this case, we will be using a Dancy-Wolf decomposition, which means to reformulate the problem, and this is called the master problem. So here we have, I don't know if you see my pointer here. Do you see it?
Yes.
Okay. So the original problem is like the original formulation. Then we will be reformulating it as a master problem. So this reformulation usually changes the selection of variables. For instance, so far we were using vertices and edges. And this formulation we will be using like the whole independent set, meaning that the solution is described closer to the structure, to its structure, but describing the solution with the structure involves many more variables. Actually, it's not even polynomial anymore, it's exponential. And because it's exponential, we need to look at a restricted master problem in which only a subset of the variables, which correspond to columns, if you look at the prime in the matrix form. So we will be using, we will be interested in a selection of columns. And to do that, we have like a property that any optimal solution is based on the limited number of columns corresponding to non-zero variables in the original formulation. So then we do not need to account for all other potential columns which are in exponential number. It's good news because it makes the problem worse in terms of complexity, in terms of number of variables. We will solve a relaxation of this of this restricted master problem. Then we will use the dual variables to price the solution of a subproblem. And this subproblem will actually find new columns with a negative reduced cost for a minimization problem. And in this case, if it finds one, this column will be added to the restricted master, and we will go on until no other improving columns can be found. And then we will ask ourselves, is the solution integral in the relaxed form? If it is, then we are done. Otherwise, we will go for the standard branching, in which we will again use this technique. So obviously, it's quite long. If we go for the full branch and price process, especially because the column generation is at the root node, but also during all the branching procedure. Usually, we don't go that far. We we use the solution from the column generation at the root of the branching tree, and then we fix the variables and we solve it. And that's a heuristic, but usually it's much better than solving the original problem formulation. So that's what we did with the quantum algorithm. So here, that's what I tried to say earlier, but that was not, that was out of the sequence. So we have different options to use the quantum, the QAOA as a heuristic. We use it to solve the restricted master problem first, and that would give us a better integer solution. That would be like a heuristic. That was done proposed in the literature. What we did is to integrate QAOA in the pricing step, so as a subproblem. So the advantage of using option 2 is that the pricing subproblem is purely combinatorial instead of including a continuous variable as well, and for which quantum algorithm are studied like MaxCut, knapsack, maximum independent test, and short pass. And in our case, the subproblem would be a maximum independent set. Also, we could expect the QUBO to a simpler QUBO for the subproblem with less constraint relaxation. We know that including more relaxation would be more difficult to be solved with QAOA because it would include more local minima, and we could consider our QA as decomposition, like an algorithm on a quantum processing unit separately. So what we did is that we had like the restricted subproblem. We solve a linear relaxation. We retrieve the dual value for the pricing problem. And in the pricing problem, we use first a classic heuristic, like Desature as a greedy heuristic. Then we try to use the quantum algorithm if it improves the solution. And if we cannot find a better improving column, then we check with the exact algorithm, especially because to prove optimality, we don't need at first to use the exact algorithm, but at least we need to make sure that no improving column exists. So if we can find the improving column with a classical heuristic, we save time, which is good. So usually we use a classical heuristic and exact, and instead we could use in the middle the quantum algorithm as an RQAOA solver. Okay, so in the case of the graph coloring problem, if we wanted to solve a compact linear formulation, we would use the formulation on the left, which is quite bad, actually. We never use this formulation, especially because it involves just too many symmetries. To just give you an idea, a permutation of color in a feasible solution leads to the exact same partition. So the branching bound is quite ineffective. So for this reason, it's just impossible to use this formulation. But if we want to still have a compact linear formulation, there's no other way around. So for this reason, we want to go for a non-compact formulation, relying on defining a partition of graphs vertices as independent sets. So basically, the solution, the formulation is quite simple. We want to find independent sets. Basically, that's all we say. And S is the set of independent set, and it contains all independent sets which are in exponential number. So that's where that's where the trick is. And actually, we will be using in the relaxation of this problem the dual variables value, which will be used in the pricing subproblem. And in the subproblem, we find the maximum independent set, which is to maximize a weighted independent set, because we use the price of the dual variable for the graph coloring problem. So this will be solved with a branch and price scheme, especially because of the non-compact formulation here for the coloring problem. So we wanted to take benefit of the RQOA algorithm when it outperforms the heuristic. So what we did is to define an improvement ratio, which is quite tricky to understand. So I try to make it clear, actually. So first, we have the number of pricing calls where the heuristic failed, but RQOA succeed to find an improving current. And then we have also the number of cases, so that would be the green. Then we have the number of cases where an improving solution exists. And then that would be the combination of the green and red. And in the experiment, we used this improvement ratio, so the ratio between the green and red to define the RQOA improvement rate. And in simulation, we obtain a result for here two types of density of graphs. So for graph of density 0,1, the classical heuristic found an improving column in 95% of the pricing rounds. And in 5% of the remaining rounds, RQOA found an improving column in 75% of the pricing rounds, when such a column exists. So it's quite difficult to see what it means, but basically, because the QA, the quantum algorithm is embedded into the decomposition scheme, and also to find improving currents, it's not quite obvious to define how it helps. Obviously, the full branch and price scheme is really time consuming, and usually, as I said before, we are not using it in its full version, but instead we use it as a heuristic, but with a guaranteed quality. Because what I didn't say at first is that when we use a column generation, with the reformulation of the original problem, is because it improves the quality of the bound, and then we obtain better relaxation, and that's what helps to increase the size at which we could solve the problem with a good quality. Okay, so as a concluding remarks, some takeaway message. So first, we propose a generic hybrid quantum classical decomposition scheme for solving a difficult combinatorial optimization problem. The concept is quite general, and it could apply to different optimization problems. The application was to graph coloring problem involving a maximum weighted independent set as a problem as a subproblem. So we focus on the smart charging scheduling example, but it can be extended to other problems. And even with the same kind of constraints, it could apply to another problem in energy management, in particular, when we need to schedule nuclear outages. We have exactly the same constraints. Because we have a set of dates for an outage for a plant, and we have also overlapping constraints between two outages from the same site. So this is exactly the same group interval scheduling problem. Of course, there are other constraints, but this is part of the problem. We also define the generic hybrid quantum classical branch and prior library to benchmark other quantum algorithms, especially because they could be used in place of QAways for a large class of integral linear problems. So the perspective would be to improve solving the MIS with RQAway or other quantum algorithms to be less sensitive to instances. Of course, this is a general problem we have when solving a combinatorial optimization problem. No techniques can use all of the instances corresponding to a prime. Usually there are classes of instances. A technique can better solve with respect to the others. But in this case, it was not consistent, so we will need to improve. And we will need also to benchmark this type of quantum hybrid decomposition scheme with other quantum algorithm and other problems, obviously. Okay, so that would be all.
Thank you, Pascal. Okay, so I will take over and share my screen. Okay, so thank you, Pascal, for sharing this with us. So it's question time now. If you have a question for Pascal, you can either ask it in the chat or raise your hand, and then you can ask your question. So do we have any question for Pascal? No? Oh, there is one raised hand. Yeah, Wesley.
Hello, it's
Yes.
Yassine. It's Yassine, not Wesley. I don't know why the raised hand is attributed to Wesley. Anyway, it's Yassine Agouchi. Thank you for the presentation, Pascal. I really appreciate. I have one question about the penalty tuning when you convert the ILP MIS problem to QUBO. So did you tune the penalties manually, or there is a certain study or method behind it?
Pascal? We've lost Pascal. The other Pascal, I mean.
Yes.
Sorry, maybe.
Oh, it's because you muted me. So
No, really? No, I don't think I
yes,
did.
because
Or
it says that you muted me and I couldn't.
I'm sorry, I didn't mean to do it.
Okay.
I probably pressed the wrong
Wesley,
button.
could
Sorry,
you repeat the
Pascal.
question, because the
Yes.
sound was not loud enough and I couldn't hear you distinctly, please?
Of course, yeah. And is the sound okay now?
A little bit better,
A
yes.
little bit. Okay, I will try. So yeah, my question is about how do you tune the penalties when you convert your MIS ILP to the QUBO? Do you use a manually tuned method, or there is a certain study behind this penalty tuning?
Actually, there is a study behind the choice of the penalty. I gave the reference we used for this part of the job. But actually, I did not do the study at the time. So
Yeah.
that was the work of Margarita Veshchezerova. She did in her PhD, so I cannot for sure answer the question. But the reference is included in the slide.
Okay.
We could check it, but we used a reference to help finding a good choice for the penalty.
Okay. Okay.
I
Thank you,
included the
Pascal.
reference in the slides.
In the slides. Okay. Thank you very much.
Okay, and can we access the code? As far as I know, the code will be available once the deliverable is published. Is that it, Pascal?
I think so. I think that Joseph will send you the package because
Yeah, so the
is...
code will be published. It's in deliverable 5.10, if I remember well. So it will be on our website, but that's at the end of October.
Okay.
Is Joseph here?
I guess he is. I think I've seen.
I've seen him. I'm trying.
Yes, I think so.
Yes,
Oh,
he
yeah,
confirms
yeah.
the code
Okay,
will be delivered at the end of October. So
yeah,
stay
sorry.
tuned. It will be on our website, on the NEASQC website, on the page dedicated to this use case.
Yep, that's it.
Okay. Any other question? No, I don't see any other raised hand. It's not very easy to see the raised hand, so I'm double checking to make sure I don't miss anyone. Well, Pascal, is there anything you wanted to add, or can we close for now?
Well, I just wanted to add that the code is generic, but it's not optimized in terms of the best result we could obtain in the classical counterpart. But the reference we used for this work is provided, so it could be improved. But that was not the focus here, to tune finally the classical part. But the reference, which is the reference in the literature, as the best result for this solving the graph coloring problem is also provided.
Okay. Well, thank you very much, Pascal. So if there is no other question, I don't think there is. I think we will close for now. So we'll have another webinar in October dedicated to QRBS. And if you're attending this webinar, you will get an email announcing the exact date so you can register. So I will finish with thanking Pascal for sharing this with us all today, and hope to talk to you soon in another NEASQC webinar. Thank you, everyone. Thank you for attending.
Thanks, Pascal.
Bye.